Hello everyone, my name is Shaman Narayana. Welcome to the presentation of our paper Deadlock-Free Design Assurance using Architectural Formal Verification. Almost all of you would have come across the ask from your management to prove that there are no deadlocks in the design. Am I right? Even though this ask appears to be trivial, it can easily turn into a complex and an unsolvable problem as the design gets bigger and bigger. In this presentation, we are going to discuss how architectural formal verification provides a solution to this difficult problem using three simple steps. First, let us look at the planned agenda in this presentation. We will start with the description of the problem, which is proving no deadlock in the system and the significance of the same. We will use a complex system of lossless hardware compression IP as an example to further relate to the problem statement. Then, we will describe the challenges associated with verifying the requirement of no deadlock in the design using both simulation-based and formal-based verification methodology. Later on, we will provide an overview of architectural formal verification. We will once again use the example of lossless hardware compression IP and provide step-by-step instructions on how to embrace the architectural formal verification. From there, we will go over the results that shows clear impact of leveraging architectural formal verification along with the case studies of the logic defects found by the architectural formal verification in our example of lossless hardware compression IP. In the end, we will wrap up the presentation with the learnings and a quick summary. Before diving into the problem statement, here are some terms that we'll come across in the presentation that we would like to expand on at this moment. Formal property verification, aka FV, PSV standing for pre-silicon verification, which is also known as dynamic simulation-based verification. Architectural model, AFV standing for architectural formal verification, and so on. For these, we will be using respective acronyms throughout the presentation. Now with this, let's get into the introduction section and understand the importance and challenges associated with the requirement of a deadlock-free design. A deadlock in the design can lead to a denial of service, also known as DOS attacks. Let's consider the scenario in the picture where an attacker gets access to a request type that can constantly put the system, in our case server, in a hang state. Due to this, the server will not be able to service requests from legitimate users. This will appear as service denial from the server to the user, which is also referred to as denial of service attacks. Now, to prove that there are no deadlocks in the design, pre-silicon verification will require many test cases targeting specific conditions. This works against the challenging and non-negotiable design delivery schedule, as we all know. One can think of leveraging the standard formal verification methods of writing assertions, assumptions, and proving them at the system level. However, this is not effective due to the exponential complexity. Let's understand this a little better using lossless hardware compression IP as an example. Here is a high-level micro-architectural diagram of a lossless compression IP. In the simplest form of working, a hardware compression IP consumes uncompressed data stream as input and produces compressed data as the output. User configures the IP from a pool of valid configurations and then sends the uncompressed data stream as the input. The input FIFO, also referred to as the ingress FIFO, consumes this variable length packets and sends out a fixed length packet to the match logic. The match logic identifies best possible matches and sends the result to entropy generator as well as the symbol buffer. Based on the compression format selected in the configuration, the entropy generator generates entropy. Once the entropy generation is complete, the symbol buffer sends the symbol to the symbol encoder. The symbol encoder encodes the symbol to the specific entropy and sends the encoded symbols, which is also known as the compressed bit stream, to the next stage of bit-to-byte packet. Here, the compressed bit stream is converted to the byte packets and sent to the egress FIFO. From the egress FIFO, the user reads the compressed data stream. The end of the input data stream is indicated by an end of the request packet. When the IP receives the end of the request packet and has completed processing all the input data, it has to assert the complete signal. This is important for our today's discussion, that the IP has to assert the complete signal after processing all the input data and it has received the end of the request packet. Any errors detected while processing the data are sent to the error handling and control logic, which get forwarded to the ingress FIFO. Upon receiving this error signal, ingress FIFO will start dropping any input packets except the end packet. Now, the no deadlock in the system requirement translates to proving the lossless hardware compression IP must assert the completion signal for every end of the request packet, irrespective of any error. Let me reiterate that. Irrespective of any error, the no deadlock in the system requirement translates to proving that the lossless hardware compression IP must assert the completion signal for every end of the request packet. Now let us look at the challenges associated with this task. For a hardware compression IP, the uncompressed stream is considered as a stimulus. For n bytes of uncompressed data, this translates to 256 raised to the n possible combinations to verify. This significantly increases the number of input combinations to verify. Now, since the various input data combinations dictate the flow of the control signals within the design, for the completeness, it is necessary to verify all input combinations, which is 256 to the power of n. Lastly, since an error can occur at any cycle in the design, crossing this with the number of input combinations further increases the number of test cases. Putting all this together, we can see that deploying PSV, pre-silicon verification, to prove no deadlock in the design appears to be a mission impossible task considering the short runway to deliver the product. Hence, we decided to leverage standard FPV methodology of developing assertions based on the requirement and proving them. We deployed traditional FPV methodology and tried the bottoms-up approach. We consulted the FPV tool experts to confirm that the tool engine settings were optimized. However, it quickly became clear that with the large complex design, this pursuit would not give us the results that we are after. Assert 1 in the table describes our system level requirement of no deadlock. This assertion made minimal progress even though we ran the tool for 24 hours without any interruption. We decided to do the reachability analysis using cover properties to characterize the design state space. We considered different stages in the design as end target for reachability analysis. For an example, cover property 2 in the table describes that we are able to pass the input packet from ingress FIFO to the match logic. Cover property 3 in the table shows that the match logic sends the processed data to the entropy generator. Cover property 4 describes if the entropy generator is sending the entropy generation complete signal. Lastly, cover property 1 is looking at the reachability analysis of the entire pipeline and also acts as a witness property for assertion 1. As we can understand from the table, we are not able to achieve the reachability for all the cover properties that we described. Hence, we move towards applying architectural formal verification approach, and my colleague Bhushan Parikh will talk more about this methodology and our findings. Thank you.
Thank you, Shaman, for a quick yet in-depth explanation of the deadlock-free design requirement and challenges associated with proving the same. Now let's dive into the architectural formal verification methodology. This methodology is a three-step process comprised of development of architectural models for the targeted RTL blocks, replacement of the RTL blocks with the developed architectural models in a formal environment, and prove the no deadlock requirement property. And step 3, compliance check of the architectural model against the respective RTL block. If a mismatch found due to an architectural model, then fix the model and go back to the step 2. Let's understand these steps one by one in detail. Step 1, developing the architectural models. In this step, we are modeling the behavior of the selected RTL blocks using the system Verilog assumed properties. The goal should be defining properties for the behavior that is essential for the no deadlock system level requirement. For example, interface signal carrying control information such as valid, complete, etc. should be modeled as part of the architectural model, while no abstraction is required for the interface signal driving the data or payload. Let's go through the exercise of developing an architectural model for the ingress FIFO as an example to further understand this concept. If you recollect, the ingress FIFO consumes variable length uncompressed data stream packets and sends it to the match logic. In addition, in an event of any error, the FIFO drops all the packets except the end of the request packet. This translates to 6 atomic requirements. Number 1, the FIFO must forward packets to match logic if there is no error. Number 2, in case of error, the FIFO must drop all packets except the end of the request packet. Number 3, the FIFO must drop all subsequent packets after the completion signal is asserted. Number 4, as a FIFO, it should never overrun or underrun. Number 5, the FIFO output data length must match with the valid data bytes in the payload packet. And number 6, the FIFO must not corrupt the data. Now, if we take a closer look at these requirements, then the first 4 requirements are control specific, while the last 2 requirements are the data specific. Hence, while developing the architectural model for ingress FIFO, we should only develop the system Verilog assumed properties for the first 4 requirements. Modeling of data-dependent requirements, meaning requirement number 5 and requirement number 6, is not necessary. The next step is to replace the RTL block with the respective architectural models. In this step, we'll replace the RTL blocks from our formal environment with the respective architectural models. Now, care must be taken to not go overboard and replace all the RTL blocks. Instead, replace only complex RTL blocks and leave the relatively simple RTL blocks as it is. For example, symbol encoder, bits to byte packer, and egress FIFO were relatively less complex blocks in our design, so we did not model them. Another important point is not to replace the RTL block for which we are trying to achieve the proof. Example given, in our design, the error handling and control logic block had most of the control signals, making it the key block for formal proof. Hence, we did not develop model for it either. Now, once we have our formal environment ready with architectural models, we can start proving the no deadlock requirement and debug the failures. In case, if we achieve the formal proof for the property, we cannot use it for the sign-off unless we complete the most important step 3, that is verifying the architectural model and RTL blocks. In this step, we are required to validate the assumptions which we use to build the architectural model. As if one of the assumptions is not valid, then it might be possible that after fixing the assumption, we find logic defects in the design. Now, due to less complexity at the block level, we can deploy the traditional formal verification methodology for proving this assumption properties. In cases where there is a little more complexity involved, we can address it by leveraging various design reduction techniques. Example, reset abstraction, free variable parameter reduction, etc. During this process, after the changes made to the architectural model due to any mismatch, we must go back to step 2 and ensure the validity of the proof for no deadlock requirement. Now let's go over the results we achieved after embracing this methodology. With the help of architectural formal verification methodology, we were able to achieve full convergence for our no deadlock assertion property at the system level. We were able to accomplish this task within 30 minutes. That is in contrast to inconclusive results after 24 hours of runtime using the traditional formal verification methodology. In addition, we were able to cover the scenarios described by cover property 3 and cover property 4 in less than 10 minutes. Impressive, isn't it? Not only this, but we were able to find multiple logic defects in the pre-silicon verification sign-off design. Let's look at some of the logic defects as case studies. Defect number 1. Now, based on our microarchitecture of the lossless compression IP, the symbol encoder done signal must assert after the symbol buffer empty signal and delayed by a 1 clock cycle. Also, the encoder done signal must be sticky high, meaning once asserted, it must stay asserted until the next configuration packet is received. In almost all the PSP cases, we observe this behavior. However, while running the architectural formal verification, we found a case where the symbol encoder done was behaving as a pulse instead of a sticky high signal. After some investigation, we identified that the failing behavior requires a specific rate at which packets are sent to the IP and read from the IP. Now let's move on to the next case study. In this logic defect, the error handling and control FSM missed covering a specific error case. Let's call it as a defect error case. Now, due to this, there was no handling for this error, leaving the system in a deadlock state when this error was asserted. Again, We were able to discover this logic defect using the architectural formal verification. After spending some time debugging the failure, we learned that the missed error assertion requires the repetition of a specific input pattern at various intervals. For an example, 50 clock cycles followed by 3 clock cycles. So then next we started studying behavior observed in the pre-silicon verification environment. During this analysis, we found that the pre-silicon verification was exercising the pattern correctly, but not at the required interval. Either it will have interval of 0 or it will have fixed interval of 50 clock cycles, but not a variable interval that we were looking for. Now, since our design was PSV signed off and we really wanted to get a characterization between the architectural formal verification and the pre-silicon verification, we did further investigation. So for the first logic defect, we updated our pre-silicon verification test bench to have a random rate of pushing the data to the IP and pulling the data from the IP. After this update, we were able to consistently hit the logic defect within 1 month of continuous execution. For the second logic defect, we conducted a review of pre-silicon verification coverage and found that the toggle coverage exists for the signal associated with the missing error case. So then we reviewed the test cases targeting this error. From the review, we found that the error injection mechanism was used for error testing, and there was always multiple errors present in the system. Due to this, system was always able to exit gracefully due to the other errors, even though the error handling logic was missing a case for the defect error case. Now let's go over some learning from our experience with architectural formal verification. The development of the architectural model can be an iterative process and will require additional time. Hence, advanced planning is required for the successful execution. Verification of the architectural model against the respective RTL blocks is a must for completeness. And only proving the system level requirement defined in the step 2 is not enough. We recommend executing architectural formal verification methodology in the early phase of the program, as this methodology may identify potential gaps in the architecture. In summary, system-level deadlock logic defects are extremely elusive, especially for complex designs such as our lossless hardware compression IP. Pre-silicon verification and traditional formal property verification methodology may not be effective in proving the absence of such defects in the design. Using the architectural formal verification methodology, we were able to identify all logic defects in the design and formally prove that there are no deadlocks in the design. Since the architectural models are describing the behavior and are agnostic to the implementation, the architectural formal verification methodology can be scalable across derivatives and or other projects. Thank you very much. Any questions?